My name is Stéphane Vidry. I'm the Executive Director of ILSI Global, and it's really my pleasure to welcome you to our third session on innovative packaging for our 2021 ILSI Annual Symposium. Before we start with the speaker, just want to mention disclaimer that the views expressed in the following four presentations are solely those of the speakers and do not necessarily represent the views of the International Life Science Institutes. Also, I want to mention that each speaker had the total freedom to prepare her or his slides. So it's now my real pleasure to welcome Dr. Carballo. She holds a PhD in chemistry from the University of Ottawa, Canada, with a dual doctorate in the area of natural product chemistry and medicinal chemistry. Dr. Carballo is a professor at the National University of Costa Rica. It's also my pleasure to welcome Dr. Gude, who studied food chemistry in Berlin and followed with a PhD in the area of veterinary drugs at the Federal Health Service in Berlin. He is the deputy head of the Swiss Quality Testing Service, and not least, he is the chair of the ILSI Europe Packaging Material Task Force, which organizes next year its 7th International Symposium on Food Packaging. So this is really a big event, welcoming about 300 delegates. So maybe, Thomas, I yell to both of you, to Anna and to you, but maybe you want to say a few words about your upcoming symposium.
Yes, it's a pleasure to speak to you here. You're welcome. And as you see on the slide, it's really our pleasure. Now, with more or less than 2 days, 2 years delay, we planned it for 2020 last year already, but due to the pandemic situation, we had already certain shifts, as you may see. And now it's clear we will in any way organize in May 2020 as a physical meeting, hopefully with a lot of participants and many people allowed to travel then anymore. And that's in principle the 4-year top event in packaging materials, packaging issues not only in Europe, I guess it's worldwide. And it would be a pleasure to welcome you at this event. Hopefully you can join physically. Thanks.
Okay. So back to you now. I yield to you.
Oh, we want to start now, yeah? So maybe Anna, then I will hand over to you. Ladies first.
Okay, thank you. Thank you, Thomas. Thank you, Stefan, for the presentation. In this first speaker, we're gonna have Carolyn Lock, and she's an engineer with a degree in paper making. She's active in research and development projects related to surface treatment of paper boards and development of new food contact materials with specific barriers properties. And this morning in my country, in afternoon and evening, and probably in yours, she's gonna have a talk on the road towards fully cellulosic barrier materials, possible alternatives to plastics. Hello, Caroline, and welcome.
Hello, Anna. Hello, everybody, and thank you very much for inviting me to speak today at this symposium. As mentioned, I will talk to you about the road towards fully cellulosic barrier materials and possible alternatives to plastics, and of course, welcome questions at the end of the presentation. You should see my presentation now. So just to mention that 2 of the projects that I will mention during the presentation have received funding from the bio-based industry joint undertaking under different grant agreements. Before going into the, let's say, subject itself, I wanted to say a few words in one slide about CTP. We are an industrial and technical center serving its industry, which is the pulp and paper industry, with the goal of creating value to strengthen the positioning of the pulp and paper industry all over the world. And to do that, we try to contribute to the development of the product mix by working in new market, developing new paper functionality and new process technologies, and working as well with the downstream sector, for example, the food packaging sector. And we do that through advanced industrial research, which is exploratory, some innovation, technology transfer through consultancy and expertise services, and analytical services as well. So as mentioned today, I will try to give you a bit of context about the search for alternatives to plastic materials, why we are looking for that now, and present to you two processes that we hope could lead to materials of the future and to hopefully fully cellulosic barrier materials. Those two processes are the wet lamination of microfibrillated cellulose and chromatogeny, before concluding on this presentation. So, but first, a bit of context. You are probably all aware of current regulatory context that is shifting more and more. And for example, the Single-Use Plastic Directive is part of this context, in which producer responsibility is extended. Reusable solution to single-use plastics are supported. Reduction targets are very ambitious, and some bans on some materials are also implemented through this directive. This is one example. Another one is specifically in France, the law that's called the Egalim law, which targets a balance of commercial relations in the agricultural sector. It also targets to promote healthy and sustainable food. And specifically in relation to plastics, it targets the decrease of plastic uses in the food sector. For example, through forbidding trays to cook, reheat, and serve food in collective catering, through forbidding plastic straws, through forbidding plastic bottles in school cafeterias. So those are strong actions from Europe, from different members of the Union that target plastic packaging. But that's not only coming through regulatory context. Pressure is also applied from consumers, for example, because more and more consumer awareness is rising, in part due to a strong media coverage of littering, plastics in the ocean, and so on. And NGOs and foundations have more and more strong action to accelerate the transition to a circular economy. So the trend that we see is really trying to shift away, or at least partly shift away from plastic materials. One possibility to do that, and I'm not saying it's the only one, of course, but it's one of the possibilities to go towards cellulosic materials, because cellulose is a bio-based polymer, renewable, biodegradable, recyclable, so a really strong contender to shift towards packaging that are part of the circular economy. Unfortunately, if it were that easy, we would have done it long ago to switch, for example, from plastic bottles to paper bottles. This is just here one example among many others. And there's been a lot of communication recently in the media about the possibility to shift to paper bottle. But it's not just about producing, for example, a bottle that is made from paper. There is a lot of requirements to take into account to produce a packaging material. We won't describe them all here that are listed on this slide. This is not the goal, of course, but it is just to tell you that it is very, very complex to create a packaging material that answers requirements both for protecting the food, managing converting, sealing and recyclability, biodegradability, visual aspect, mechanical resistance, and so on. There are many, many factors to take into account. If we go into more details in the barrier requirements, which is one of the requirements that packaging has to answer, then we can see that there are many requirements in terms of barrier depending on the food that is packaged into the packaging material. Some food need barrier to be protected against water vapor, against oxygen, light, aromas, contaminants, and so on. So the combination of the product that is packaged and their shelf life and needs to be taken into account in order to define the barrier specification that's needed for a packaging material. All of this to say that even if paper and board are very good in terms of an environmental ranking, because as I said, it's a renewable, biodegradable, recyclable material. On its own, before converting, barrier performances that are required for most food products, most foodstuff, are not achieved, and substrates need to be transformed, converted with a barrier solution in order to achieve the requirements needed to be able to package foodstuff, for example. And here you can see on this graph that the vast majority of barriers that are used today on paper and board are extruded polymers, mainly fossil-based, plastic-based, petrol-based, sorry, aluminium, wax, silicone, fluorinated products, so materials that are not sustainable or not integrated in a circular economy. And the trend that we see more and more is how to try to phase out aluminium and polyethylene and to replace those barrier coatings, those barrier layers with bio-based materials in order to have paper and board packaging that are bio-based, composed as much as possible of fibers that could be recyclable in a paper stream, paper recycling stream. How to remove fluorinated compounds from paper and board, and really the question that we, I think, are asked really often now is it possible to produce a 100% cellulosic packaging with the technologies today? And this is what I'm going to try to answer, or just give you hints about today. At CTP in the recent years, we have worked on two specific barrier technologies that we hope are barrier technologies of the future, and that bring good barrier performances to papers and board substrate without adding plastic materials on top of it. The first one is called microfibrillated cellulose wet lamination. And this technology is a process that deposits and dry a layer of MFC at the surface of paper and board. I will go a bit in more detail on the technologies right after. And the second technology is called chromatogeny. And this one is a process that chemically modifies the cellulosic compound, so the cellulose substrate, in order to turn it hydrophobic. But let's go into a bit more detail on MFC wet lamination first. MFC, or microfibrillated cellulose, is a product that is produced from cellulosic fibers. But these microfibrils have a small diameter and small length. They are fibrils, really, and they can be used as a coating layer on top of paper and board in order to obtain an excellent barrier to grease, to oxygen, to contaminants, and to aromas. As you can see here on this picture on the right, you have an uncoated board which has been put into contact with oil for 30 minutes. So of course there is a big oil stain on the board after contact, and on the right picture, the exact same board coated with a layer of microfibrillated cellulose. And on this material, after 30 minutes of contact with oil, as you can see, the barrier is perfect and there is no staining of the oil on the material. So the barrier is really excellent. And the advantage of microfibrillated cellulose is that it is, of course, cellulose, so a bio-based material, biodegradable, recyclable in a conventional paper recycling stream, like paper and board, but with the additional advantage of bringing barrier. The drawback, however, of this MFC material is that it's manufactured as a gel, so it has a very low solid content of about 2 to 4%. So the rest is water. But it's highly viscous. So traditional coating processes that are used in the paper making industry are not adapted to apply it on papers and boards. And it was therefore necessary to find a new process, a new concept to be able to deposit this microfibrillated cellulose layer on the paper or board substrate in order to obtain this barrier. And this is where the MFC wet lamination process came to life. So the idea is that the wet MFC film is formed by filtration of the MFC through a wire. And only once this MFC film is formed, then it is reported on a paper or board substrate. And since it is still wet, it then naturally adheres to the paper substrate. So there is no glue that is used to join the MFC layer to the paper or board layer. It's all natural adhesion. And the paper on which the MFC film has been applied is then simply dried before being rewinded. And you then have an MFC stratified paper at the end of the machine. This technology, so as I said, is targeted to bring excellent grease, oxygen, and contaminant barrier to paper and board. MFC are cellulose, a very hydrophilic material, so it does not bring either water barrier or water vapor barrier. This is not the target of this kind of layer. And up to now, the technology has been developed at lab scale to begin with, so at technology readiness level 3, and is currently being at pilot scale, sorry, on a small pilot machine that's been installed at CTP at the end of 2019, so a bit more than a year ago. And it requires therefore dedicated equipment to develop the process and produce sample for testing and proof of concept. And this MFC laminated material is afterwards fully compatible with further surface treatment to bring other barrier performances to it, such as coating, laminating, and so on. To give you a bit more detail on how the material is produced at laboratory scale, here you have the equipment that is used, and the idea is simply to filter an MFC suspension on a wire using some vacuum. Then to replicate this MFC film on a paper substrate. And then using a plating press that you see here in the middle to press the MFC film and paper together between blotting papers in order to join the two layers and then to finish drying the material using conductive drying under stress, for example, in a flat dryer or in a half moon dryer. And then when you peel the blotting paper, you have the remaining MFC wet laminated paper. To go into a bit more detail about the performances of the paper, because I mentioned we can reach excellent oxygen, grease, and contaminant barrier. I've shown you the grease performance, but here you have on the right the oxygen transmission rate that we can reach with an MFC covered paper. And as you can see, with MFC laminated paper using about 16 to 18 grams per square meter of MFC, then we reach barrier performance and OTR at 23 degrees and 50% relative humidity, which is in the range of 2 to 5, so quite a good performance, bearing in mind that the initial substrate showed absolutely no barrier performance to oxygen at all. And the addition of the MFC film is possible both on mineral coated paper or on directly paper itself or board itself. It really depends on the surface chemistry of the material, but most paper and board show good addition to with this MFC film. I also mentioned that the barrier to contaminants is excellent. And here we have done some evaluation of the transfer of contaminants through the barrier by using a donor sample that was spiked with selected substances. And here the selected substances were MOSH and MOA surrogates, so mineral oil surrogates. And as you can see, the migration of these contaminants was reduced through the barrier by more than 90%. On the red, on the graph, you see the migration without barrier, and in green, you see the migration through the MFC layer, which was significantly reduced. So that was MFC wet lamination. And as you can see here on this picture on the right, this is an MFC film that is being peeled from paper or board substrate. So this is what an MFC wet laminated material looks like. Then the second process I would like to talk about today is chromatogeny. Chromatogeny is a green chemistry process that brings hydrophobicity to hydrophilic reactive substrate. This can be papers and boards, this can be lignocellulosic fibers, polyvinyl alcohol, starch, some minerals, for example. And it's a solvent-free technology that is suitable for ready-to-reel processes. The first developments in the paper industry have been applied to papers and boards, and the idea there is to bring water resistance to the material while keeping converting ability, recyclability, and biodegradability of the material. It doesn't change those properties. And it can also be applied to coated papers, for example, polyvinyl alcohol coated paper, in order to protect the sensitive, water-sensitive barrier. As you may know, polyvinyl alcohol is also a hydrophilic material, very soluble in water. So to protect this barrier from moisture, still keeping the recyclability and biodegradability performance of the material. So the basic principle of chromatogeny is to use the reaction of fatty acid chlorides with hydroxyl group in order to obtain fatty esters that are grafted on the paper. So the idea is there to protect the water-sensitive material by crafting a fatty alkyl chain, so starting from a fatty acid chloride on the surface of a layer that contains an hydroxide group. Here you can see that the fatty acid chloride reacts with the hydroxide group, and that an ester bond is formed with the material. And in order to do that, the fatty acid chloride is deposited as a liquid on the material in the range of 0.2 to 0.5 gram per square meter, so a really very, very low amount of fatty acid chloride, which is enough to get this ultra-fast solvent-free reaction and hydrophobize the paper. So as you can see here on these two examples, this is a paper that's been treated using chromatogeny, that's been first coated with polyvinyl alcohol and then grafted using chromatogeny. And we see that it is perfectly hydrophobic. So the water rolls on the surface of the material without wetting it, and that the oil here, it keeps the barrier to grease, and the oil does not penetrate into the substrate. Chromatogeny has been developed now up to industrial scale, specifically in South Korea, where there are 2 industrial machines. The first one was started in 2015, and the second one started in 2018. And before that, it was invented in 1997, so it took quite a few years to bring it first to lab scale and then to pilot scale in 2010, sorry, before moving on for different projects to bring it towards industrial scale. The main target and market of these technologies are uncoated papers and boards. So the idea there is to really improve the water resistance of cellulosic-based material. For example, to manufacture waterproof paper. Here you have some example of markets that can be imagined for such material, such as simply corrugated board that would be resistant to rain, some health and medical paper, filters, paper that can be used for agriculture, so for working outside but don't get wet, paper that selectively absorb oil but not water. Those are all applications that can be imagined. As for polyvinyl alcohol coated papers and board that can be crafted with chromatogeny, then the idea is to develop medium and high barrier performances for this material. And here we can imagine applications such as release paper. This is actually the target of the industrial machines in Korea. Baking paper, sacks and bags, cups, for example, can also be an applications. So there are plenty of ideas and markets for such material with those performances. And speaking of performances here of grafted papers and boards, here are some numbers of the barrier performances and other performances that can be reached. As you can see on uncoated papers, then the idea is really to improve the hydrophobicity of the material, so to really lower the water absorption capacity and to bring a high water contact angle of the material. And on coated PVOH coated paper and board, then the water absorption capacity is even more significantly reduced. So we have an excellent barrier to water, excellent water repellency. We keep the excellent grease barrier of the polyvinyl alcohol, and we get actually at 23 degree and 50% relative humidity quite good water vapor barrier, which unfortunately is not that good in tropical conditions. So these are things that should still be improved. And this material, thanks to the polyvinyl alcohol layer, is also an excellent barrier to oxygen and mineral oil. And as I mentioned earlier, this does not change the recyclability, biodegradability, sealability, printability of the paper substrate. Food contact compliance is ongoing, so we are investigating this. So to conclude on these two processes, I would like to mention two European projects in which we have worked on these different processes. The first one is SharePact. It's finished last year, so it ran from 2017 to 2020. And in that project, the idea was to develop a renewable, biodegradable, and recyclable flexible paper-based packaging material. And in that project, wet lamination of microfibrillated cellulose was used in combination with coating of biopolymer in order to reach both oxygen contaminants and water vapor barrier performances needed for such packaging. And the second project is called Cellulosic and is ongoing. And there the idea is to target a high barrier all cellulose packaging materials, so using both MFC wet lamination and chromatogenic grafting to produce 3 different proof of concept that you can see here that are clamshells, cups, and trays. You can find more information on these 2 projects on their websites. So as you saw, we have different technologies, processes that could bring interesting barrier performances to paper and board substrates without requiring the use of plastic materials. These are chromatogeny and MFC wet lamination, which target different barrier performances, water for chromatogeny, grease, oxygen, and contaminants for wet lamination. That can be used in combination with different barrier coatings to bring additional barrier performances, for example, to water vapor, because this is not really targeted by those 2 technologies. And that in the future, and this is really the objective, could really be combined together in order to bring all the necessary barrier performances to paper and board substrate in order to really produce fully cellulosic barrier material that don't require the use of polymers, and to possibly replace some of the polymers that are currently in use on the market. So to conclude, I would like to say that we really hope that paper and board are one of the packaging material of the future due to its strong appeal for circular economy, for answering environmental concern, being bio-based, biodegradable, recyclable, being safe to put in contact with food, and being easy to transform and convert in order to form packaging. So thank you very much for your attention during this presentation, and I'll be happy to take a few questions.
Thank you, Caroline, for the presentation. We have one question. It says here if it has been analyzed, if there is any interaction between the MFC and code and the future content. For example, can the content of vitamins and minerals interact with those coatings?
So if the MFC layer interacts with the food, for example, that is packaged, is that the question? We strongly believe that the MFC layer, once it is formed, is extremely coherent, and that the MFC cannot be separated once they are dried, so that there is absolutely no risk of microfibrillates being separated from the layer and migrating into food, for example.
Thank you. And I have a question myself. I was wondering, I'm sorry, probably it's not my field of expertise. I was wondering if these coatings will affect the biodegradability of the material?
That's a very good question, and they don't, in fact, and that's really why also there are strong processes and technologies, because we have done during these two projects I mentioned biodegradability trials, and biodegradability is absolutely not affected by either MFC layer or chromatogeny.
Thank you. Thank you very much for the presentation. Now I leave Thomas with the next speaker.
I guess we still have 2 or 3 questions. Do you see that in
sorry.
the panel? Or maybe we have still a little bit of time. So,
The other, I saw people asking if there was a possibility about making the presentation in Spanish. I said I will ask. Maybe with the recordings we can have that. And then I have 2 more questions here. Are there any? Sorry, it's really tiny. Is there any comparative studies conducted yet on how different packing methods affect the nutrient content of foods being packaged? That's one. And I think it's related to what you mentioned, but if you wanna say something about it.
Sorry, could you repeat the question, please?
Yeah,
I'm not sure I understood.
Sorry. Are there any comparative studies conducted yet on how different packing methods affect the nutrient content of foods being packaged?
That's a very good question, and I have to admit is completely outside of my field of expertise.
Okay.
I'm sorry I can't answer.
Oh, that's fine. I have a second question from the same person. How adaptable are these methods, or can they be integrated with more simple methods, such as packing food in plant leaves? I can repeat the question.
Yes, that's a good question as well. Packing food in plant leaves, is that what you said?
Yeah, like how adaptable are these methods, or can they be integrated with more simple methods, such as packing food in plant leaves?
Well, I'm not sure if you are packing food in plant leaves that you are really targeting barrier performances of materials. So maybe it's not really necessary to bring additional processes and technologies on leaves, to be honest. But speaking from let's say scientific point of view, plant leaves are cellulosic materials, and you could, I guess, apply chromatogeny on them and it would work.
Okay. And there is another question here. Are you developing any work on the paper chemistry to improve the barrier properties?
We are mostly working on barrier layers, not necessarily directly on the paper chemistry, but chromatogeny is affecting directly the paper chemistry by grafting fatty acids directly onto the paper. So in that sense, yes, we are carrying out indeed work on paper chemistry to improve barriers. Okay.
I don't know, Thomas, if you see any more questions. I think we have covered.
Yeah, there's one specific question, I guess, but that is related to page 17 of your presentation. Is there solvents used for MFC suspensions?
No, MFC suspensions are in water, so it's completely water-based, no solvents.
Okay, then it's clear. Then the last question I saw here, I believe it was already mentioned that the investigation is ongoing. But what would be the main challenges in confirming these materials are apt for use as food grade or food contact materials in regard to the food safety aspect?
That's a very good question. We have no concern for MFCs as some grades of microfibrillated cellulose are authorized for food contact. As for chromatogeny, we have no particular concern as well for food contact, because we are talking about grafting fatty acids that are palmitic acid basically on paper and board, and palmitic acid is can be eaten. It's a food additive. But since we are grafting it on the paper and board and creating a new product through chemical reaction, then it needs to be proven that this material is safe, and we need the authorities authorization. But intrinsically, we believe there will be no problem to get this authorization, and we are working on it.
That's good. Believing is always good. Maybe
Exactly.
the last question before we move to the next speaker is, do they impact freshness of packed material?
Freshness of packed material, that's a very good question.
Yeah.
I'm taking that question as do they impact the shelf life, I would say. And it all depends on the barrier level that is targeted. Do we have very good barrier performances? Yes. Are they on par with plastic materials that are found today on the market, or even aluminium barrier? Not exactly. So shelf life might be a bit lower with such materials. Indeed.
Okay, great. Thank you. I guess you answered so far all these questions showing up in this question box. Maybe if you have a chance to look by yourself, and maybe you can add some direct answers, that would be perfect. If not, we can come back to that at the end. So there is a question box, and maybe you see that. Then we are done with the speaker, and maybe you can bilateral answer if you like. It's up to you. Huh? Thank you very much for your.
Thank you.
Yeah, thank you very much for your great talk. So now we see Nathalie a second time. Now, now we can switch to our next speaker. It's Natalie Gonta. Gontard, is that correct? Yeah, pronunciate it. Yeah, no. Yeah. And she is research director of INRAE, not as mentioned at University of Montpellier anymore. She changed her function. It's a job, I guess. And she is still well known and is working for European Commission sometimes, and as also for the EFSA. And she's now talking about fighting plastic pollution with innovative food packaging. So let's see how successful your fight will be. Nathalie, you have the floor.
Okay, can you see my screen?
It's perfect. Yeah, otherwise I would complain. I do not complain, so you can start.
Perfect. So good morning or good afternoon. No, good afternoon or good evening, everybody, according to where you are. So I would like first to thank Stéphane Védry for inviting me. Stéphane is a former colleague from the University of Montpellier in France. And also I would like to thank also all the organizing committee. So I will give you a few words about how innovation in food packaging can help fighting plastic pollution. Okay, here is the first slide. So we know all that food packaging is a key actor of food consumption, and this is a very important element of processing, storage, transport, marketing, and also consumption between the field and the plates. But now we know also that there is another step that is a little bit less positive. This is after usage step, up to waste management, and up also to final, as we will see a little bit later, as up to the final fate of the materials. So now we all are facing the issue of balancing the positive impact of packaging materials for reducing food waste and losses, and on the other hand, the negative part, the negative impact of packaging materials, and especially in our environment. And this is really one of the main issues we are currently facing, and this is also one of the reasons why the previous speaker, Carolyn Lock, has just presented us these materials, which are bringing new benefits for the environment. So maybe let this the food packaging has 3 key steps on its life cycle. And if the benefit is mainly during the usage through its functional property, which of course should be adapted to the food preservation, the negative impact are mainly during the production of this packaging and of course after the usage of this packaging materials. And we know that plastic packaging are bringing some very specific issues which are linked to the fact that these plastic materials have a very specific behavior, which that is very different from all the other materials humans have used up to now. They are not able to slowly solubilize like metal or glasses, for example, to remineralize water and soil. They are not able to biodegrade like all organic matters in order to reintegrate the carbon cycles. They have a very, very specific behavior, and plastic materials are able to fragment, to persist a very long time, because this fragmentation take a very long time. They're able to diffuse, and once they've reached the micrometric size, they can diffuse everywhere in the compartments, the environmental compartments. And once they reach the nanometric size, they are able to translocate, which means to diffuse inside, to pass through the barrier of our organs, and to diffuse inside the organs of living beings. And the results is that usually it means that life cycle environments are systematically and unfairly underestimated the environmental impact of plastic, and therefore favor plastic compared to all the other materials, whether they are papers, metal, glass, and so on. So in our laboratory, we have decided to set up a strategy to develop new materials, what we call innovative materials, that are not presenting the issue of fine particle pollution. So the objective is really to develop materials that are fully biodegradable in natural condition at the very end, which means that they are presenting zero risk in terms of particulate plastic pollution, fine particles pollution of plastic waste. And we have also decided to work only on non-food raw materials in order to not compete with food usage. And for that, we have used agricultural residues as raw materials for the production of polyhydroxyalkanoate. In fact, this is PHBV, butyric valerate, as a biosourced materials, but non-food sourced, which is bioprocessed. It is fully biodegradable and it can be biorecyclable. For the time being, we are really working on making this PHA material, PHA-based materials, more resistant for being able to be reused and recycled also via mechanical recycling process. Okay, so this is according to the Plastic Europe figure. In Europe, you can see that there is about 1/3 of our plastic packaging wastes that are incinerated, 16% landfilled, 13% non-collected. There is only a few percent that are closed loop recycled, and then the rest that is called recycles, in fact, they are either downcycled or exported. So at the end, if we look at the fate of our materials, this is more than 61% in Europe of our plastic packaging waste that are ending in our environments and are increasing our reservoir of micro and nanoparticles. And our objective is really to increase this part of biosourced and biodegradable and biorecyclable also materials, to increase this green here, this green arrow of materials. So here it is. This is an example of materials we have developed. We used agricultural residues. On one side, we are using liquid effluent like cheese whey or water from oil washing and different type of agricultural residues as a fermentation substrate for the production of PHBV. And on the other hand, we are using solid wastes like wheat straw, vine shoots, and so on, that are going ground and in order to produce lignocellulosic fiber-based fillers. Both are compounded together, and the structure is tailored in order to obtain the required mass transfer properties, which means water vapor barrier properties, oxygen properties, but also carbon dioxide properties adapted to the food preservation. Because for each food is requiring very specific properties, and having the highest barrier possible is not the good solution for food. And the result is that we are currently using plastic barrier films that have too high barrier, and we are micro or micro perforating them. So each materials need to be adapted to the requirements of the food in order to increase the shelf life of the food and reduce food loss significantly. And then the materials obtained here, we have an example of these trays, are fully compostable in natural conditions, which means that you can put it in your garden and the material will fully disappear in a few months in order to reintegrate the natural carbon cycles. For the production of this PHA, we have developed a combined process coupling two-step anaerobic digestion for the production of biogas and digestate. And this two-step anaerobic digestion is also producing, in addition to biogas and digestate, VFA, volatile fatty acid residues. And these volatile fatty acid residues is used for the PHA production. And this here, you can see the pilot plant that we have developed in Verona, in Italy. This is the Innoven companies. This has been also financed by the company, but also, of course, in the framework of a bigger project, which is a European project. And by coupling this production of PHA with biogas and digestate, it means that we are able to increase the added value of all the agricultural residues, okay, and also to facilitate the development of such type of process also at local scale. This PHA are mixed with lignocellulosic fibers in order to decrease the economical cost, but also the environmental cost of our trays, and to tailor also the barrier properties, the permeability, I would say, of our trays according to the type of food we are intending to pack with. And the mixtures of PHA and lignocellulosic fibers are shaped with commonly used thermoforming processes, industrial thermoforming processing. In fact, this is injection molding simply. In some cases, we are using some specific additives to give some additional active and intelligent function to our materials. Here, this is an example of oxygen absorbing additives we have developed based on synthesizing nano iron on nanoclays, and the additive is then dispersed within the material itself during the shaping process, and there is a very efficient absorption of oxygen and therefore an increase of the barrier properties of the materials when necessary, of course, only. Currently, we have produced these materials at the I would say pre-industrial scales in different type, in different shape. We have tested also these packaging materials on different food with fresh fruit and vegetables. Of course, it was the easiest, but also with fresh cheese actually, fresh meat, and also fresh poultry. These materials have been developed in the framework on 4 different European projects. The first one was EcoBioCap. It was handed about 5 years ago. The second one is the NOAA project, which means no agricultural waste. This is in this particular European project we have developed the coupled process with anaerobic digestion of PHA production with anaerobic digestion. We have also made some scientific and technical advances in the Residures project, which was not coordinated by INRAE but by the University of Roma. And here we have made some advances in order to use other residues than agricultural residues for the production of these materials, and especially by using urban residues, both for as effluent for the PHA production, but also for the production of lignocellulosic fibers. And we are also currently going on developing this material, especially by adding some intelligent and active function in the framework of the GlowPack project, which is also a European project. And all these materials have been developed using multi-scale approach, where there is 3 main scales which are used. The first one is the material engineering scale, where we are studying the material itself at the different scale, molecular, nano, micro, and macro. The second scale is dealing with mainly with the food packaging system. They are mainly including process engineering modeling, which means that here we are considering the packaging with the food itself and how this packaging is able to answer the requirement of the food in terms of barrier properties, active, for example, antimicrobial properties, and so on. And the third scale is the scale of the stakeholders themselves, where we are taking into account the industry's requirement, the consumers and end user requirement, but also environmental aspects. And here we are developing what we call knowledge engineering modeling. And all these scale are coupled. This is an example of what we have developed, a multi-scale structure mass transfer prediction systems, where we are developing modified atmosphere packaging according to the different type of packaging extra, a simulation of modified atmosphere packaging with the food itself, and then a multi-criteria querying able to, when associated to packaging database, to be able to rank packaging solution according to the requirement of the different stakeholder, which means that you will say, for example, I want a material with this permeability of oxygen, this permeability of water, vapor permeability, but I want a cost lower than X euro per kilogram. I want a transparent or not a transparent, and so on. And currently we are using this tool, this decision support tool, for eco-designing our materials, and we are also working on translating all the output of this decision support system into more comprehensive environmental impact. And this is an example of environmental score, global score we have developed, that is taking into account the raw material origin, the food losses reduction, so its efficiency and its necessity to reduce food loss. And the third parameter is about the material end of life. And for each parameters, there is a score which is indicated according, for example, if the material is renewable, not renewable, from competing with food and so on, and etc. Okay. And that's all. Thank you for your attention.
So now it works. Yeah. Thank you very much, Nathalie. Thanks for your excellent presentation. If I look to all those nice questions, currently not that many questions showing up, but there's still the opportunity to raise your question even by writing and typing. Maybe I can just ask a simple question, but that's related to one of your last slides. You mentioned this eco score. Maybe I did not hear it correctly, but it looks like very similar to the Nutri-Score, which the food industry is using. How can I, as a consumer, can I differentiate, or I have to expect now on the packaging, on the food packaging, a Nutri-Score and an eco score, and look similar? What is the intention here?
Yes, exactly. It's very close. The main difference with Nutri-Score is that Nutri-Score is mainly based on life cycle analysis, which means that Nutri is for food. Okay, now there is another score taking into account packaging, the impact of the packaging material on the environment also. So it's a combined score of the food environmental impact, food health impact, but also packaging aspects. In our side, we are just working on the aspects of environmental impact of packaging, because we are considering that the health aspect is already taken into account by the legislation. Okay, and we are also going far beyond life cycle analysis, because as I just explained in the different in the first part of my presentation, life cycle analysis cannot take into account the most important environmental impact of plastic packaging, and this is why we are going far beyond this the conclusion of life cycle analysis.
Okay, but maybe at the end you have not enough place on the packaging to give all your messages from the content and from the packaging. That's always a fight packaging suppliers.
It can be for the consumer. It can be also for not for the consumer. It can be also for the users, or depending. But I agree with you that this is really an issue also that can.
Yeah. Okay.
Just
The future
will
show that,
but not too simple, because if it's too simple, it becomes also not really informative. So.
Yeah, for sure. Then many people will complain in a different way. But here's just a short question. Can you clarify the difference of the process with the PHA produced by Danimer?
The PHA, I'm not really aware about the Danimer process, but the main difference is that Danimer is using food raw materials as for the production of the PHA, which means that they are using either like Canon company also producing the same PHA. They are using mainly food resources like starch or sugar or so on. In our case, we are not using food. We are just using agricultural residues. And for the know-how process, we are combining the anaerobic digestion with the production of PHA, which means that from agricultural residues, thanks to this coupled process, we are able to produce biogas by digestate, which is a fertilizer, and PHA also. So this is really like cascading and not only refinery, but bioconversion of agricultural residues in an optimized way. And this is also enlarging the type of agricultural residues we can use, which means that even if they are really rich into very resistant lignocellulosic contents, we are also able to treat them thanks to this process.
Okay, we can take one last question here. Can these biodegradable trays be thermosealed with a high barrier lid? Question. An example, the case of fresh meat, fish, etc.
Yes, we are also working on these aspects. We have developed a very specific thermosealing system. So yes, of course, it's possible. It's not so. It's relatively recent that we have an industrially applicable, very efficient sealable system. Yeah.
Okay, great. Then you only have to go to market. Sounds good.
It was one of the issues, yes. But before finding it on your supermarket, it will take some time because
sure.
you know that upscaling is really is a real challenge. Then you can discover many barriers that you have to overcome, and it's not so easy.
Okay, yeah, for sure. Great. Thank you very much for your answers. Then I guess we may go on with our third speaker. So Anna, it's again your turn.
Thank you. Our third speaker is Marianelli Esquivel. We're going to switch continents. We're going to America, and she's from my country and my university. Marianelli is an industrial chemist with a master's degree in forest product science, and she's going to give us a talk on renewable materials obtained from agriculture and aquaculture residues. The lab where Marianelli works in Costa Rica has a long trajectory on the use of agriculture and aquaculture residues for destruction of natural polymers and for the use of them in different setups. So welcome, Marianelli. Thank you for the presentation.
Thank you. Can you see my screen?
Yes.
Okay. Good morning and good evening. Thank you so much for the presentation, Anna.
Marianelli, we cannot see your screen. You're organizer.
Now you can see it, right?
Yes, now we can. Thank you.
Okay, thank you. Thank you so much for the invitation to share some of the work we do at our laboratory. As Anna said, we work at the National University, Universidad Nacional. I work at the Polymer Science and Technology Laboratory. Those are some of our facilities. Costa Rica is a really small country located in Central America, and we have 5 state universities. Universidad Nacional is one of them, and we work at the chemistry department. This is the building, the new building of chemistry, and we belong to the Faculty of Exact and Natural Sciences. So I'm going to show a little about the work we do in the laboratory with residues. We have 3 main research areas: composite and nanocomposite materials, converging technologies, nano and biotechnologies, and we extract biopolymers like collagen, chitin, chitosan, starch, and cellulose. And we have these main objective of using residues. We use different type of agriculture residues. Today I'm going to talk about specifically about pineapple and aquaculture residues, mainly so a skeleton of crustaceans, mainly shrimp. About agriculture residues, as I said, the pineapple case, well, is a big issue in our country because, as you can see, this is a pineapple plantation. It's a really extensive area cultivated with this plant. And Costa Rica is one of the main exporters of pineapple, fresh pineapple worldwide. It represents an important economical activity. The main destination of this pineapple are USA and Europe. And for every fruit that you can get, you leave a complete plant of pineapple in the field. I'm not talking about the crown, it's the full plant that stays in the field. So that means there's a lot of biomass that stays in the field and gives some environmental issues. Per hectare of pineapple cultivation are produced 300 tons of rastrojo, that is the leaves and the stem of the plant. And for 2018, it was more than 40,000 hectares plant. This biomass has a high volume and slow degradation. And the main processes applied are chemical drying and soil incorporation. This is the pineapple rastrojo in the field. The biomass, like I said, is a huge amount. It's mainly composed by cellulose, hemicellulose, and lignin. And the cellulose, I'm not going to talk about cellulose, but for the pineapple leaf fiber, the main component is cellulose. So it becomes an emergent source to obtain cellulose from agricultural residues. We have been extracting micro and nanocellulose and try to find some applications for those materials. Micro and nanocellulose have some properties like high mechanical strength, very absorbing, light, non-toxic. The fibers has a high aspect ratio and elevated surface area and high thermal stability. Some applications we have been exploring are hydrogels, electronics, thinking about electronic paper, filtration system for water purification, films, and composite materials. Those are some pictures from the work we have been doing. For the pineapple leaf extraction, we take the leaves. We usually focus our attention on the leaves, not the stem. And we do mechanical processes that is called decryptication. Then we do like a soaking process, and then we do a bleaching process. And we get this material that looks really similar to cotton. From this material, we extract microcellulose. The microcellulose extraction is made by a controlled acid hydrolysis. So you eliminate the amorphous regions and you keep the crystalline regions. It's not an extensive hydrolysis, it's a mild hydrolysis. So you keep these structures that has these crystalline and these amorphous parts. We have been preparing microcellulose and PLA composite materials. PLA is well-known polymer. It's a aliphatic linear polyester and is compostable under certain conditions of humidity and temperature, and can be easily consumed by microorganisms. Okay, let me move this. For the microcellulose, we did a thermal analysis. As you can see, the thermal stability increases when you go from the pulp to microcellulose. For the infrared analysis, usually we focus on these areas to look if the lignin and the hemicellulose was removed during the first processes. And also we do X-ray diffraction to analyze the crystallinity index. The idea is that when you go from pulp to MCC, the crystallinity index increases. It goes from 35 to 70%. Also, here are some images of the pineapple restaurant or the leaf fiber. As you can see, we have the fibers. There's some porosity because the treatments we applied previously. And then we have the microcellulose. As you can see, these are bundles of microfibers. And here you can see a fiber. Then we prepare this type of composite materials with different amounts of MCC. These materials, I don't know what I'm talking. I'm touching something. Let me see. Okay, I have this window. We applied some pretreatment with terbutanol and polyethylene glycol. Pretreatment increased the nucleation capacity and interfacial interaction, as well as the compatibility. About the thermal analysis, as much MCC is added to the material, the thermal stability increases. And the range of temperature of degradation is between 290 to 400 Celsius degrees. Also by DSC, it was shown that the melting heat decreases and the crystallinity decreases. And from DMA analysis, the dynamical mechanical analysis, the storage models increases. Also, we did these same images before and after the fracture, applying this mechanical treatment. Before the fracture, you can see the surface, and then you have these images after the fracture where you can see the fibers coming out of the matrix. This implies that maybe the interface between the fiber and the matrix can be improved. In the case of nanocellulose, nanocellulose can be nanofibers, NFC, which maintains the amorphous and the crystalline parts. The diameter is between 2 and 20 nanometers, and the length can exceed 10 micrometers. It's a long fiber. And for the case of NCC, nanocrystal cellulose, by an acid hydrolysis and extensive acid hydrolysis, you can separate the crystalline parts. The diameter is smaller than NFC, 8 to 20 nanometers, and the length can be from 100 to 600. The NFC extraction we applied for the pineapple leaf fiber was mediated by the tempo oxidation first. The tempo oxidation is a specific process to oxidize the hydroxyl groups in carbon-6, and then we apply grinding process with a Masuko grinder and homogenization, and then microfluidization. By this process, you can get this type of hydrogels. And for the NCC, as I said before, the hydrolysis is an extensive hydrolysis. So you get this suspension after dialysis, where you keep the crystalline parts. And as the process is made by sulfuric acid hydrolysis, you get these sulfonate groups on the surface that improves the water dispersion and gives a negative charge in the surface of the fibers. For the characterization, we did AFM, TEM, FTR. And also we analyze size and set the potential for the case of NCC. Those are some AFM images. Also, I put here the size. This is for NFC and this is for NCC. As you can see, the size of the fiber is different. Here you have length about 1 micrometer and width about 3 to 5 nanometers. For the NCC, the size is about 700 nanometers and the setup potential is minus 34. Like I said before, has negative charge. Also was applied same analysis, is similar. For the NFC, you can see this network of fibers. And for the NCC, you can see the needle-like small parts. From the thermal analysis, as expected, the thermal stability increases by extracting the NCC. Goes from 355 to 376. That is expected because you keep the crystalline parts and eliminate the amorphous parts. Also, we use this NCC material for starch matrices to make composite materials. This starch is extracted from this bitter cassava that is not used for eating. It's not eatable. And here are some pictures around the optical and SEM images of the starch granules in this variety of these. Here are some images of the materials obtained. Those were characterized also by thermal analysis. The range of thermal decomposition is between 340 and 345. It's a small range. And for mechanical properties, as you can see, as much NCC was at the tensile strength increased, the maximum amount was 15%. And for the elastic modulus has a similar behavior, more NCC, higher elastic modulus, and the higher amount was 15% of NCC. Also for this material was made water solubility analysis, water vapor permeability and transmission, and opacity. Also were applied some antimicrobial activity for some bacteria and some fungi, and it gave interesting results for application in food. Also, we prepared nanocellulose films. Here we applied 2 different methods. One with tempo oxidation as a pretreatment, and then ultra-trurex is an homogenization process, and we get this suspension. And also we apply Mazuko grinder, and you get this pulp is like the paper pulp. And then by microfluidization, you get these hydrogels. We did a process to get these films similar to the process applied for paper, and we got these samples. This is bleach. It's quite transparent, and this is unbleached, so it keeps the lignin. The idea was to compare if it is necessary to apply a bleaching process. Also, this depends of the application that we are looking, of course, but the idea is to compare these materials. This process of microfluidization and Mazuko grinding were made in Aalto University in Finland. One of our students went to Finland to do the process. Here you can see some AFM images. This is for NFC, and this is for the film prepared. I think this is the bleach material. And you can see the network formed by the nanofibers. Finally, I'm going to talk briefly about our aquaculture residues. Mainly, we work with the shrimp shell that becomes a residue in the aquaculture industry because the shrimp is exported without the shell. We apply on first chitin is a polysaccharide really similar to cellulose, and it has 1/3 of minerals, 1/3 of protein, and 1/3 of chitin. This chitin can be extracted by eliminating the minerals by acid treatment, and then protein by alkaline treatment. We get this material, this is chitin, and we have a pilot plant where we do this process. Then the chitin is converted to chitosan by the acetylation process in this reactor. So we modify the structure to get these functional groups, primary amine groups, that makes that chitosan can be soluble in light acid media. That has some advantage. This is our pilot plant. We can process about 300 shells per batch, and the yield is about 20 to 30%. For the case of chitin conversion to chitosan, the yield is about 50 to 60%, and per batch we can process about 5 kilograms. Some application for chitin and chitosan, well, for chitin the applications are less. Mainly have been applied as a nematicide for soil preparation, and also from chitosan you can make fibers, control release system. This is my chitosan microparticle, chitosan based emulsions like flocculant agent for water treatment, because the amine group can be charged positively. Also as a particle stabilizer, for example, for gold nanoparticles, and also for chitosan, you can get these films or three-dimensional structures. For the case of films, can be made by casting. Actually, this is a composite between chitosan and collagen, also extracted in our laboratory. And as you can see, it's a film, a transparent film. Those are some images of the film. And also you can get these tridimensional structures by lyophilization. And in this case, we studied the release of an antibiotic, thinking that this material can be applied in the skin for burns. Also for chitosan and other applications we have been exploring are the chitosan nanovesicles, and also the chitosan nanovesicles as like a mini reactor to get gold nanoparticles. Here are some images of the anisotropic gold nanoparticles that also can be applied for some applications, for example, as a detector of different substances that have been explored. And also chitosan, you can get this type of bead. Those are beads between chitosan and iron. Those beads were applied to arsenical removal in water. So has a lot of applications. Thank you so much for your attention. I would like to thank to all the institutions that make possible the research that we do in our laboratory. And as a conclusion, I can say that we have this great potential to use residues from agriculture and from aquaculture residues to obtain these materials, renewable materials, to get different applications. Thank you so much.
Thank you, Marianelli, for your presentation. It was a really good presentation of the work the lab has done. I have one question, I think, from Filomena Silva. How sustainable and environmentally friendly is tempo oxidation of MFC?
Okay. When I first thought about NFC, I didn't talk about tempo, but we didn't have the equipments. We are trying to get the equipments to do the process completely mechanical and to avoid the use of chemicals. For example, tempo in Japan is really popular. Also, they already have these applications for ink in pencils. I don't know if it is really sustainable, but it's really used for NFC. I think let me see, lately is focused more on mechanical extraction, not chemical. So that is a challenge for us to get the equipments to do that in our laboratory.
Thank you. I don't see any more questions on the board. Do you, Thomas, see any more questions?
No, from the question board, it looks like that you convinced everybody listening to you. That's
Okay.
the way it is. It's good. Yeah, then maybe we go directly on. Thank you very much. And then we come into our last speaker is again a lady. So we have today a lot of ladies. It's only me here. I'm the outlier a little bit. Doesn't matter. So now we have the pleasure to listen to Carolyn Orfila. I hope I pronounced it correctly. Otherwise, correct me. And we're switching again continents before we switch to Costa Rica. Now we're going back to Europe and China because the talk deals with compostable packaging, technical possibilities, consumer attitudes and behaviors in the UK and China. Interesting comparison. So, Caroline, you have the floor.
Thank you very much. Can you see my screen?
Yeah, it looks perfect. But you may have to go into presentation mode. Yeah.
Yeah, I will do that now.
Yep, looks perfect.
Okay. No, sorry, no, I don't want to leave the seminar. Is that okay?
Yeah, looks great.
Thank you very much for the introduction, and thank you for the organizers to give me the chance to present some of my work today. So yes, I come from the University of Leeds, and I am co-leading a project called Citrusave, which focuses on the valorization of byproducts from the Chinese citrus processing industry. And today I'm going to tell you a little bit about this project and some of the innovations in packaging that were realized, but also will focus most of my talk on a survey that we did on the consumer attitudes and behaviors towards recyclable and compostable packaging in the UK and in China. So the Citrusave project was an academic industrial partnership project involving academics from both the UK and China and industries from the UK and China. So from the academics perspective, there was the University of Leeds, Zhejiang University and Zhejiang Gongjiang University, and we were funded by the BBSRC, the Newton Fund and the Ministry of Science and Technology of the People's Republic of China. The academic side, the industrial companies, including Parkside Flexibles, Caracol, Biopowder, and two industries in China called Joyful and Huayu. And the industry partners were funded partially by Innovate UK, which is the innovation agency for the United Kingdom. So the global issues that we were trying to address through Citrusave was to reduce food loss and waste, as we know that a third of food that is produced is lost or wasted before it's eaten. And packaging has a really good role in preventing some of this food to be lost. And just reminding you that wasted food represents a waste of resources in terms of the land it's needed to grow it, the energy, the water, the labor that goes into it. But also that disposal of food waste also poses a burden to land and aquatic environments. Through Citrusave, we were also addressing food safety, again, a place where packaging has a big role to play. And we do know that you know, around 1 in 10 people in the world will fall ill after eating contaminated food, with a loss of many millions, loss of healthy life years. And finally, we were looking at dietary health. We know that obesity and overweight are rising worldwide, and a lot of this obesity can be attributed to poor diets. And these poor diets are characterized by low fiber intakes, where in general, across UK and China, we see 30% lower intake of fiber than recommended, and high intakes of saturated fat. So I will take you a little bit through what we did in that aspect as well. So the project was organized in terms of valorizing these waste from the citrus industry and looking at food safety in terms of formulation, using byproducts from the citrus processing industry as natural additives and preservatives. But also a big component was packaging, either using the materials directly to make packaging or as active materials or coatings on already existing packaging. And we have already heard some of that aspect, how it's done in the previous talks. And then through the health aspect, we had a branch that looked at utilization of these byproducts in skincare, which I'm not going to talk about today, and also application for functional foods and supplements. So it was quite a large program of work, but I will tell you a bit more about the packaging later. Why the citrus processing industry? Well, actually, China is now the biggest producer of citrus fruits in the world. The annual production last year of around 39 million tons of citrus fruits, and about half of those are mandarins, citrus unshu. The processing industry generates about 1 million tons of solid waste streams, primarily as peels, but also pips and other solid residues, and 2 million tons of liquid waste streams. How are these waste streams produced? Yeah, I will talk about this later. So we start obviously with the mandarin fruit, which is then peeled manually, actually, to have the segments. And we have then the peel waste, which we can use as a resource. The segments are then separated, again, manually, and these are soaked in an acid bath, where we get some of the membrane around the mandarin removed and the production of this acid extraction liquid, which is this liquid you can see here flowing through these pipes. The segments are then soaked in an alkaline bath, which will remove the remaining of the membrane, and you will generate an alkaline extraction liquid. These segments are then canned, or they can be put into bottles like this one, okay, and then exported and enjoyed throughout the world with a very good and long shelf life. The extraction liquids can be combined, and that neutralizes the liquid, and the liquid waste is then treated with ethanol to precipitate some biopolymers, and then you end up with some ingredients which are reusable in several applications. I should say that this liquid waste has high chemical oxygen demand. So currently China has some legislation that says that this liquid waste, because of its high chemical oxygen demand, cannot be disposed in in natural water or in natural land. It has to be treated somehow. And therefore, this way of recovering the biopolymers is a way to reduce the chemical oxygen demand and actually valorizing some of that so-called waste at the same time. And the quote I had in the previous slide, was one from a colleague who works in environmental management, who told me, waste is not waste, it's just resource in the wrong place. And we really took this to heart, to say, actually, these are not waste streams, they are resource streams that we can then valorize and utilize. So the aspect I'm going to talk to you mostly today is the peel aspect, where the peels can be shredded and dried initially because they are very wet, so they decompose very quickly. And then we applied micronization to make powders of different particle sizes that can be then extracted using green methods, so mainly water-based methods, dried, and we obtained various extracts which are then used. So we had food-grade powders and liquid ingredients that were either used to produce cosmetics, and there is a line of cosmetics currently being commercialized in the United Kingdom. We also have various edible formats, including gels, emulsions, and films. The gels and emulsions were primarily used as ingredients for fat replacement. And then we had a packaging stream where the ingredients were mainly incorporated as coatings on the surface of compostable packaging. And compostable packaging now comes in many different substrates, so you can get different properties of the material, as we've heard earlier, but these can be functionalized then with different properties. So the packaging aspect was done by a company called Parkside Flexibles, which is quite near here in Wakefield, near Leeds. And they develop different packaging solutions. And they are very much at the forefront of developing compostable packaging material. And there is a accreditation in the United Kingdom around how long should it take for a packaging to decompose or compost in a home. So here you have an example of a snack that is packaged in compostable material, and you can see that over 6 weeks it will then break up. You can see it breaking up here eventually to little pieces and starting to disappear into the compost. Okay, and then you can see actually some of the asparagus actually still there after 6 weeks. So it seems to be fairly well degraded over time. And we know that this approach can be helpful in reducing plastic particles in soils, which, as we heard earlier, are a great environmental concern. And a study in Italy showed that composting packaging material can reduce particles in soils from 20% occurrence to 1.5. So it can be quite effective. So as part of the Citrusave project, we explored different packaging morphologies, if you like. We were looking primarily at things that have short shelf lives, including bread, which is one of the most wasted category of food in the United Kingdom. We also looked at some high-risk products, including fish and chicken. We looked at ripening of fruits, and we also started looking at ready meals. And ready meals are interesting. Actually, all of these are interesting because often they have more than one packaging component. And so you have to look at not just one, but several packaging components, often a see-through one to allow the consumer to see the product. And then you have something else that you can print on. So in the case of ready-made meals, they often have a cardboard sleeve with all the information on it, and then you have a tray that is holding the product. But we do know that packaging has a strong contribution to reducing food loss and waste. And in the UK, manufacturers are looking at even 1 day shelf life extension could save the UK £2.2 billion per year. So it does make not just environmental sense, but also economic sense. And I'm not going to talk too much about the technical aspects of this packaging, but I'm going to tell you some preliminary results about some of a survey that we did in both China and the UK. And the numbers of participants are quite small, but I think it started giving us some really interesting insights about what consumers think about environmentally friendly packaging. And in particular, I'll highlight the attitudes towards compostable packaging, or the knowledge of that. So the questionnaire was structured in looking at the motivations for purchasing. Will people buy it or not? Will they pay more for it? the recycling and composting behaviors. So what do people do with the packaging once it's in their home? And also rating their environmental consciences and knowledge. And I won't have time to take you through all of them, all of the aspects today, but I will give you some highlights. So one of the things that we asked them, first of all, is, are you actually trying to reduce the amount of food packaging that you buy or use? And certainly that's something that we observe in the United Kingdom, where there is a big ambition by consumers to reduce, eliminate food packaging, not necessarily understanding the impacts that might have on increasing food loss and waste, and perhaps increasing food safety risks. But we can see that 78% of UK consumers actually want to reduce the amount of packaging that they use. But they say that it's difficult for them because they have limited options available. So perhaps the best thing for them after trying to reduce food packaging is to look at environmentally friendly packaging. In China, it's actually a more mixed picture. And in China, there's actually a lot less food packaging than there is in Europe and in the US. Very few foods are actually packaged at the moment, but it's really rising very, very quickly. So the people that are trying to reduce food packaging are, 45 to 75-year-olds with bachelor degree or above, and certain, generally higher environmental consciousness, but we didn't see an effect of gender or total income. But what were their motivations? We then asked them about, would you buy environmentally friendly packaging? And, we looked at, if you buy it, what are your motivations for buying this packaging? And we can see here that the main motivation is to reduce environmental waste, which is the top answer in the UK and second answer in China. In China, we saw that reducing human toxicity was the top option. And I think there was a perception that, packaging can actually, they are concerned about the toxicity of the packaging itself, having some transfer of some packaging materials or chemicals from the packaging into the food. Well, that was a lot lower down in the United Kingdom. In terms of purchasing barriers, so why are you not buying environmentally friendly packaging? It came back to there are very few options available for me to choose from, and that was the top reason in both the UK and China. And in China, the second reason was again being worried about food safety. So being worried that perhaps the environmentally friendly packaging doesn't have the same performance as other packaging. Well, that was not a concern really much in the UK. We also asked them if they would pay more for environmentally friendly packaging, and the answer was mostly yes. Around 50% of people will pay around 10 pence more, or the equivalent in yuan, and 25% of people would pay 50p more, or the equivalent in yuan. But we did observe that older consumers are less willing to pay more. So we looked at recycling behaviors and we compared the two countries, and in the United Kingdom, most people always recycled or did it most of the time, but it was actually a lot less common in China. And when we asked them about recycling bins and facilities for collection at home, or from home rather, then that was a big enabler of recycling in the United Kingdom, while it was pretty limited in China. So a lot of people didn't have recycling bins at home and therefore did not recycle. And the motivations for recycling were to reduce the amounts of waste sent to landfills, and the other options underneath were mainly environmentally driven. In China, it was actually to reduce water pollution, while in the UK it was mainly land pollution. But for those people who recycled, they were less motivated by the government mandating that in their area. There's recycling barriers. The top one in the UK is that they're not always sure what materials are recyclable. And this is a real challenge for food packaging, where you have multiple components, some of which are recyclable, some of which are not. And people actually don't know and sometimes just throw the whole thing into the bin. And that was the second option in China. There was also some mention in China in particular about too much time and effort to wash the packaging. And that is something that we do know that before you recycle, you're meant to wash and get rid of some of the organic material to facilitate the recycling. And it can be a barrier if it takes too much time and effort. So we also explored very briefly some of the symbols that we can find on food packaging. And we asked them whether they were familiar with these. And most people were familiar with the recyclable symbol, but not so much with the biodegradable or compostable symbols. And when we did a survey of the different symbols that we could find on food packaging, particularly for ready-made meals, we found that for some supermarkets, particularly the ones that have their own branding, it tends to be quite consistent, and they tend to use this circular symbol here. Well, for some supermarkets that have more premium brands, and they have many different brands, if you like, there was a great variety of different symbols and information. And so perhaps the consumer is probably less sure about what to do with that packaging, where the information is different on different packaging, on different products. And then when we asked the participants which type of information or how would you like to receive the information, they did prefer the kind of quite simple but consistent messaging above written instructions, or perhaps more different and more different information about the materials themselves. So that was quite insightful too. And I think for me the most surprising, not but the thing that I think we need to work more on is what do people do with compostable food packaging when they have it at home. So we do know that people want to buy more of these, but do they do what they're meant to do when they have it at home? And so when we asked them, well, how do you deal with your compostable packaging, the majority of people in the UK and in China put it in the normal waste bin. And then the second segment here in China is put it in the recycling bin, which is also a significant proportion of UK consumers. And only probably about a third either compost it at home or send it to a compostable facility. And that was very small proportion, only 5% in China. So, most consumers do not compost compostable food packaging at home. Is that through lack of composting facilities, but also we identified a lack of knowledge of what is compostable versus recyclable. And I think this has already been mentioned before, but if compostable packaging ends up in the normal bin, in a landfill, what happens to it? Compostable packaging will behave like paper or cardboard and biodegrade in the top layers where there is oxygen. But essentially, it's a linear process, so it does end up as being waste. It will take a long time to recover that resource into anything useful. In terms of recycling, again, it has been alluded to earlier in earlier talks that putting compostable packaging in the recycling can cause problems. And this is particularly true for food packaging with multi-components, multi-layered parts where people might not separate everything. It becomes quite a big effort to work out what is what goes where. And some of it, the compostable one, can probably be incorporated into the cardboard recycling, but it does cause some issues. So it's not ideal really for perhaps consumers wanting to buy this compostable packaging but not doing the right thing with it. So I think the take-home messages are that people are motivated to buy environmentally friendly packaging, and that is recyclable or compostable, and will pay a little bit more for it. But they are confused about how to dispose of it, particularly for compostable packaging. And there are limited home and communal composting facilities currently in the United Kingdom or in China, which is probably making it's really limiting the ability to compost. So that is coming to the end of my talk. So just to really thank the Citrusave Consortium. So these are over here the UK participants of the consortium, but also we were with a number of, with many great Chinese collaborators as well. Our funders who provided, with the opportunity to do this project, and I want to thank you for your attention. And I will take some questions. Thank you.
Yes, great. Thank you very much, Caroline, also for this excellent presentation and what consumers can expect in the future. That's great. For the questions, maybe one question came in my mind when I listened to you and when you showed this nice fruits where you made this nice powder out of it. How do you deal with pesticides?
So the fruits that were harvested for this process have very tight pesticide control, and we did do pesticide analysis of the peels to make sure that whatever we had didn't have a high pesticide load. But it is a concern, and so you always have to check the pesticide content of your extracts, and if not, you might have to do a treatment to remove the pesticides before you micronize it or you turn it into food. So it is a concern. So you're right to highlight that, and you just have to control it at all the opportunities and measure it along the way.
Yeah, but in other words, that means when it comes to supermarkets and to consumers, and they will always raise the question about this typical environmental contaminations if you're going for this natural sources. That might be an issue.
Do you mean when byproducts?
Yeah, maybe pesticides is one topic. So if you have growing plants and wherever they're coming from, maybe you have some other environmental impacts, and that means you would have to control regularly as well this raw materials on this issue. That's
correct, and to some extent it's easier to use byproducts, as we heard also from Marianella and others before me, where you have a little bit more control of where you source these raw materials compared to, for example, using mixed waste, where it becomes really hard to know what's come into that. So I think it's having that knowledge of the supply chain and being able to measure things all the way along, and it was something that we raised really from the beginning, because it's not just a concern for food, it's also a concern for cosmetics. For example, you don't want to be putting pesticides on your skin, but they are quite tightly regulated now. Certainly in China we did not encounter many problems, and it's a big export industry for China, so they will have to comply with Japanese, US, European legislation on pesticides. So the majority of these products that you see here are actually consumed outside of China. So it's a big export product for them.
So it looks like you're enjoying these products already.
Oh, they're not too bad, but
not too bad. Okay, that sounds good. Okay. I do not see any additional questions so far, so then thanks again to you as well. So maybe you also convinced everybody to invest a little bit more money into this new packaging solutions. So maybe then we are more or less coming to the end of our session today. So maybe Stefan, it's something you want to say as a closing remark, or?
I would like to thank all the speakers, of course. I would like to thank the co-chairs, Thomas and Hannah. You did a great job. And I wanted to remind the participants that we have tomorrow, at the same time than today, a session on advance in enhancing the microbiology safety of food. I think it's going to be also a very exciting session. So I invite you to join this session. The recording of today's session will be made available to the registrants in a few weeks, and we will make this video also available to the general public early July, so anyone can again see your talk, and we try to disseminate as much as we can. So I want to thank you all again, and I wish you a very good day or good evening.
Okay, thank you all from my side to everybody, and have a good evening or good start in the day, whatever it is. Yeah. Okay, thank you. Bye-bye.
Yeah, thank you so much. It was really nice.
Thank you. Bye-bye.
Bye.
Thank you.